Okay, so let's talk about random linear network coding, right? When you do this, normally what you have is, any coding will work like this, by the way. You will have some original packets, you have some coding coefficients, and you get the coded packets out of it. I hope that you have seen this, whether this is the Reed-Solomon code or whatever code it is, there will be this coding coefficients. And what will these coding coefficients tell you? You've seen it before, right, in the butterfly. We had a little bit C1, C2, very small one. So it tells you what to put here, and there are very famous researchers like Reed and Solomon who said how these alphas should look like. So imagine it's only zeros and ones. When if this is 1, 0, 0, 1, 0, 0, that means packet 1 and packet 4 coded together is coded coded packet number 1, okay? If we have zeros and ones, that we did before with our butterfly example. Now, what you also can do is, instead of sitting down every evening with a glass of red wine and a cigar, understanding how this matrix should look like, which properties it should have, you can even take random numbers. Therefore, it's called random linear network code. Take any random number here, put it here, and you will find out it's equally good. And why is this equally good? If you have here, if you design them, what is the goal? The goal is that you don't create linear dependent entries here, right? So that's what we had before. You don't want to create duplicates. Whether these are linear superpositions or not, duplicates are bad. But if you just send any random number here, then suddenly it also works. So therefore, a lot of people don't like network coding so much because they cannot understand that random works as good as a planned code. What you have seen before was a random code, and it stays stable, while the others who were planned are degenerating. So the question is now, why nobody came up with it before? So first of all, if you just say, what kind of random number can this be? So between 0 and 1, the same amount of numbers between 1 and infinity, right? Whatever x is, 1 over x is between 1 and 0. Now, if you don't put any random numbers here between 0 and 1, there are enough of them. The problem is you will have rounding errors after a while. In embedded systems, they don't like that. So additionally, you could say, okay, I just put zeros and ones here. And this is what people tried out decades before, and they said it's not a good code. And you will learn why it's not a good code. But between only 0 and 1s, you can do something different. You can use here finite field elements. I don't know if you have heard about finite field calculations. You will learn about this in the course. The only thing what you see here is, for now, what you need to understand is a certain granularity between 0 and 1. So it can be 0, 0.25, so a quarter, a half, 3/4, right? So then you have more possibilities, more degrees of freedom, and suddenly filling up this matrix become easy. 0 and 1s ends up in something linear dependent, which means we cannot decode maybe in the end. But having more granularity there's something what we could do. Now, if you later want to decode this, there is some complexity involved with this, right? Because you need the Gaussian elimination. The complexity should be cubic. So the question is, how can we do this here? One thing, here we have 6 different packets, original packets. We create 6 coded packets. If you want a more general one, we say, okay, we can have G packets. We call it a generation. So any G packets, which defines the width of the matrix, G elements. And we need at least G entries here, right? This gives us G coded packets because you need the G. Remember the comic stripe in the beginning. But you can fill up the matrix with more random numbers, getting more up to, let's say, K out of it. And suddenly this code becomes a rateless code. So if you have seen the code history, like tornado codes, fountain codes, they were rateless. That is what Qualcomm offers now. So rateless codes where that was the only feature they had. We were rateless, which rateless means you can send more and more codes. You don't have a certain rate. A Reed-Solomon code, if you send your original packets and some redundancy, if the other side doesn't understand, you start from the beginning. Okay? And here, with the rateless code, you can continue and continue and continue. The same you can do with the random linear network coding. Okay? But there are two features, and this is the most important stuff of the code, of the course that you should learn. There are two things that a network code can do even more. So it could behave like a normal block code, as you can see here, right? So we take 3 packets and we code out as many coded packets as we want. Then we take the next 3 and make this is the block code, like Reed-Solomon. Now we are rateless, fine. We can even say as a fountain code, fine. The other thing that a network code can do, it can recode exactly what we wanted to have in the comic stripe. So not only that we can work on all the packets, but even with a subset of packets that have been already coded or partially coded, we can recode this. So there's the property of recoding, and we will tell about why this is important. And last but not least, every code, why do we do a code in the beginning? We would like to achieve resilient communication, reliable communication. So we don't want to have, if there are losses, we want to overcome the losses. But what is the price of that? Latency. Because if you have a block code, you have to wait for a certain number of packets incoming, then you encode them, and then you ship them over the wireless link. On the other side, you will decode them. Network coding is a little bit more interesting because it can work on the fly on packets as they come in and work on something like, if you look over a generation, it can combine packets together in a very clever way without increasing the latency too much, right? So we can operate inside the generation with some tricks that you will also learn here. Now, why are these two features so important? If you look at the classical coding of today, we have point-to-point coding and point-to-multipoint. Point-to-point is really what Reed-Solomon could do. Point-to-multipoint is more what the fountain codes are doing. It's very good for multicasting. When there are problems, you just continue until the last one in the stadium has it. But then there are other things that will come up. For example, a multi-hop or a multipath system. So if you think about drones flying in the air, if you think about cars on the street, they create mesh systems. And this is not point-to-point. And if you always do point-to-point to point to point to point, there's latency problems. So it's very good for the new type of architecture that we will see in 5G, for example. But even if you look multi-source, multi-destination, source is, for example, when you get video streams from different sources, when you can store data in different stuff, if you have a mesh systems, even here the code is very good. And here, top here is point-to-point again. So what is the difference here? This is classical point-to-point without latency constraint. But if you think about point-to-point for TCP, for example, in IETF they are now talking about QUIC. QUIC is a new form of a transport protocol. They also look into coding. And there are a lot of papers indicating that network code is really good for that, helping us to make the link reliable. TCP and QUIC like reliable, but they don't like latency. So how can we crack latency and resilience in one way? This is something we should have a look at.